Okay, it's time to start. So last time we were talking about Verilog all last week. I had the introduction to Verilog. And I just wanted to make a couple final comments before we move on to a new topic. We talked about structural Verilog and behavioral Verilog. The way that it usually works out is at the bottom of the hierarchy, we use behavioral Verilog. And then we use instantiation, which is the basis of structural Verilog, for building up a hierarchy. And now for creating state elements, because we said if you want registers or other kinds of state elements, that you, the way we do it in this class is you instantiate them explicitly. And sometimes you need to use instantiation if there's some available blocks on the FPGA or in the ASIC that is not supported by logic synthesis, right? We'll talk more about that later, particularly when it comes to memory blocks. The synthesis tools don't do very well, so we tend to instantiate those. Okay. So my recommendation is to favor the continuous assignment over the always blocks, unless there's no good alternative for using, if there's no good alternative, then you end up using the always block. For instance, for the case statement, if there's no case statement in the continuous assignment, right? Also, if using always block helps the readability of your code, then it's okay to use it. For instance, large nested if-else blocks tend to be clearer and easier to understand in an always block. So we talked about the no register inference policy. If you don't remember what that means, you should go back and look at the notes from last time. But this means that all state elements will be, we want you to create them by instantiating state elements from our library, registers. Right now, later memory blocks. I recommend you use named ports. It helps the readability of your code. It helps avoid bugs. And finally, Verilog is a big language. There's a lot to it. I only showed you, we really only scratched the surface here. I think I gave you all the essential pieces, pretty much everything you need to know, but there's more advanced stuff. So if you're interested in that, take a look at the Verilog standard document, right, which is linked to the web page. There's also chapter 4 in the Harris book is pretty good. It's a good source or a good reference. And your tendency will be to Google something and look on the web for Verilog examples when you're faced with writing Verilog, either for the lab or for the homework. That's okay, but be careful what you find or what you see. There's many bad examples out there. There's a lot of people who post who are not very expert. So. And we'll be talking about more details of Verilog as we move through the semester. So you'll see more stuff as we go along. And here's just the final thoughts on using Verilog and hardware description languages in general. So in Verilog, it looks like C, but it's not really C. It's a really completely different model. When you write a Verilog program or write Verilog code, you're really not writing a program. You're describing hardware. So you really have to keep that in mind. It's entirely different semantics than C. You should know that by now after seeing a little bit of Verilog. There's really multiple physical elements in parallel with parallel activities and temporal relationships between those pieces. Right? It's really more like writing a parallel program than it is like writing a C program. Right? I put this in a box because I think it's really important. A large part of digital design is to know how to write Verilog that gets you the desired circuit. So first understand the circuit you want, then figure out how to code it in Verilog. Okay? I always start with paper and pencil, and I kind of draw out the circuit I want, and then I figure out how to write the Verilog. If you try to write Verilog without a clear understanding of your desired circuit, then you're going to get in trouble. You'll get code that's hard to debug and may not do what you want. And it may not be very efficient. Okay. And I say this all the time, and I see people getting in trouble all the time because they're faced with a problem, they immediately start writing Verilog, rather than sitting back, pausing for a minute, think about the circuit, and then figure out what Verilog will give you that circuit. Okay. So really try this. I think it'll help. The other thing is be a little suspicious of the synthesis tools. Check the output of the tools and make sure that you're getting what you want. You may be making false assumptions about the relationship between what you write in Verilog and what you get at the circuit level. So it's a good idea to get in the habit of kind of checking out what you get. Right? And you can look at it, and there's methods that you can use to look at the actual synthesized hardware after you run it through the tools. So it's a good idea to get in the habit of doing that. Okay, so that's all we're going to talk about with Verilog right now. We'll return to some of it later on, but that's it. I'm going to move on to a different topic. Unless anybody has comments or questions. Okay, so today, lecture 5 is about FPGAs, one of my favorite topics. And this is kind of back to where we were before. We're talking about implementation technologies. We talked about design flows. We talked about how to do design in general. We talked about ASICs, FPGAs, processors. Okay, now we're going into more depth on FPGAs. I interrupted that whole thing to talk about Verilog because people are starting the labs, and you need Verilog to do the labs. Okay, but so now we're back to kind of description of the kind of chips we use and build. So FPGAs are a popular way to implement designs. In fact, there's probably more different designs implemented in FPGAs than in custom ASICs these days, primarily because of the economics that we talked about last time. Except for extremely high volume, because of the high engineering costs, it only makes sense to use custom or ASIC in places where there's high volume, where you can amortize the large non-recurring engineering cost, because it's so complicated and so cost-intensive to build an ASIC. FPGAs change that equation. They're easier to design with. They're cheaper to design with. But as we'll see, they're not as efficient in their use of silicon and in power and speed. So they're used all over in military things and automotive, starting even a little bit in high-volume consumer products, like maybe displays. There's pictures of cell phones here. I don't think there's any FPGAs in cell phones yet. There may not be, because this is kind of a price-sensitive market with very high volume, where designing a custom ASIC definitely does make sense. This is a board. This is the project board we used to use in this class up until about last year. This is what we use for the labs and the lab exercises on the project. Here's a big FPGA in the middle. This is a Xilinx Virtex 5. Xilinx is one of the two major FPGA producers. The other one was Altera. They got bought by Intel, so now it's Intel and Xilinx. There's a number of other companies, but they by far are the two largest producers of FPGAs. The FPGA idea was invented by Xilinx back in around 1984, I think. So here's the big chip. This board is really kind of designed around the FPGA. It has extra peripheral things. It has a video interface, has audio interface, has some DRAM on here. It has a bunch of support things, so you can build various projects out of this. Last year, we switched to a new board, which is cheaper and smaller, but just about as powerful. The FPGA on that board, this board is right here in the middle. It's upside down. It says Zinc. It's also by Xilinx, but it has the distinctive characteristic that it has two ARM cores built right into the FPGA, which makes it more flexible. And this board comes with a kind of a nice software environment based on Python. So we've been using this for about a year now, and people taking the FPGA lab, this is the board that you've seen already if you've gone to the lab. I'm going to go back and show you a little more detail about this Virtex 5. This is what it looked like on the board. If you took it off the board and flipped it over, it kind of looks like this. There's a bunch of balls. It's a ball grid array. Those are the connections from the chip down to the circuit board. So it gets mounted on the circuit board with little solder bumps. So those balls kind of melt into the circuit board and make the connection. Lots of connections, as you can see. A lot of these are for power and ground. Some of them are for clocks, and the rest are for input and output signals. If you look at the die, the chip that's inside this package, so what we're looking at here is just a heat spreader. It's a copper heat spreader. I'll show you a cross-section of this in a second. Inside is a die, which is probably about 2 centimeters by 2 centimeters. It's shown here. This is kind of an enhanced die photograph. And there's different features you can see here on the die. We'll talk about those features in a few minutes. If you look at the connection, the way this gets connected, this is the back of the circuit. That's the back of the package die, which gets soldered down onto the circuit board. On the back of the circuit board, it kind of looks like this. These are capacitors, which we'll talk about later in the semester, which are used to smooth out the noise on the power supply. If you look at a cross-section of this packaged part, this is kind of typical for large, not just FPGAs, but also processors these days. There's a substrate material, and there's the balls that you saw here, which are relatively large. These are the balls that kind of make contact with the circuit board, and they're at a pitch that corresponds to the wire pitch that's on the circuit board. There's also a set of balls on the die that are used to connect the die onto this substrate. They're at a much tighter pitch. They're on the scale of the chip. Everything is much smaller on the chip compared to on the PCB. And kind of the purpose of this substrate here is to take that tight set of connections, very closely spaced connections, and spread them out to a pitch that's more compatible with a printed circuit board. So what you see here is connections between the silicon die down to the substrate. And then the substrate has multiple layers of wiring, and it can spread out those signals and make connections to this set of balls here. It's epoxied down. Then there's this copper heat spreader that's put on top, and it's painted or coated with something. It looks silver there. On some parts, in some applications, there'll be a heat sink that's put right on top of here to additionally help put the heat out. Remember, when this is running, it's burning power, and the power generates heat, and the heat has to go somewhere. So either there'll be a heat sink here, which is fins that stick up in the air and help radiate the heat, or sometimes there's even a fan. You've seen this on CPUs, to put a fan right on the package to draw cold air in and dissipate the heat with the air. What else? I guess that's it. Oh, I just wanted to mention the die, when they're fabricated, we didn't talk about processing this semester, but the FPGA parts, as we'll see, they have lots and lots of wires. All right, so the one thing that's made FPGAs work as well as they do these days is that modern processes have lots of interconnection layers. This shows a cross-section through the die, and each layer here is a different layer of metal interconnect. So transistors are down here at the bottom, but all the connection between all the transistors is done in metal layers. The connections between the transistors, the connections between the blocks, the power, the ground, the clock, everything comes up on using all these different layers of metal. Right? So it's been possible to build very high density FPGAs, as we'll see, because of modern processes have lots of different metal layers, maybe 10 or 12 or more. Okay, so the first week we talked about FPGAs a little bit, but I'm going to talk in more detail today. FPGA stands for Field Programmable Gate Array. It's a little bit of a funny name because there's actually no logic gates per se. It can act like it has logic gates, but there's not actually logic gates in here. And I'll show you what is in here. All right, so the basic structure of a FPGA is a two-dimensional array of logic blocks and flip-flops. Right? And so here's an array of logic blocks. This would be a particularly small FPGA. But here's a two-dimensional array. Here's the logic blocks. It's labeled as logic cells here. And there's a bunch of wires. And these wires are configurable, so we can use the wires to make connections between the logic blocks. And we can define the function of each logic block to be anything we want. Okay. So there's some way for the user, you, to configure or program the FPGA to make the connection between the logic blocks and define what the function of each logic block is. Right? And that's what gives it its programmability. It's the ability under your control to program it. And we'll talk about how that works. But that's what kind of makes it programmable, and that's the basic idea. And then, so what we want to look at is the details of the interconnect and the details of the logic blocks. Okay. Before we do that, though, I'm going to kind of pitch FPGAs a little bit, why they're interesting, why I've found them interesting. I've been using them my whole career and designing them and designing tools to use them and designing applications that can use them. So it's become an important part of my research. From a technical viewpoint, for hardware and system designers, it's kind of like ASICs. You can define any digital function you want, and you can put it inside an FPGA, just like you could design a standard cell ASIC to do that. Right? The difference with FPGAs is that you could implement a new design every few minutes or hours. If you design an ASIC, it takes you months and months to design it, and then you have to send it to get manufactured, and you have to wait. And the best case would be 2 weeks. It's usually more like 6 weeks or something before you get a chip back and you can test it. If you have an idea, you can implement it in an FPGA in an afternoon and test it right away. And if there's a mistake, you can change it and do it again. So there's a very rapid design, exploration, debug, experiment cycle, which makes it fun. When we say tape out, people know what tape out means? Have you heard that term? Yeah. Okay. So if you don't, it comes from the ASIC world. After you're done designing your chip, in the old days, we would put all the design information, which is the specification of where every wire and transistor and everything goes, and put it on a big magnetic tape, and then drive the tape down to the factory or send it to the factory. This was before the internet, and that was the way you would transfer the design. So taping it out meant you're done with the design, you put your design on a big magnetic tape and then send it to the factory for manufacturing. So that was the end of the part that the designers did. Then it was up to the manufacturers, people that have the process, to do their part. So it's kind of like here, you can tape out a new design every few minutes or hours with FPGAs. The other interesting thing about FPGAs is the fact that they're reprogrammable. You can do number one because they're reprogrammable or reconfigurable, as we say. It may actually have other advantages over fixed logic. For instance, in-field programming. So Cisco, which is a company that makes network equipment, they used to have they used to use FPGAs in their switches and routers that are used in kind of networking infrastructure inside businesses. And occasionally they would send firmware updates. They would change the function of the circuit to either adapt to new standards or to fix bugs or to improve performance. Right? So you could actually change the function of this hardware box in the field by downloading, and they would do it over the network. They could download new programs for the FPGAs. So it's kind of like an ASIC, but you can change its functionality later to fix bugs or to add features or to add enhancements. Right? That's a very kind of powerful idea. People in the research community, more than in the real world, have talked about dynamic reconfiguration. This is the idea where you could reprogram the FPGA while the application is running, right, to make it do something different. Right? Like if your application characteristics changed, right, you might reconfigure the FPGA to better match, to change the circuit that better matches what the application needs in order to speed it up. The other idea, I mean, if you have this, you could think about self-modifying hardware, right? You've probably heard about self-modifying code, where you can write a program that changes the program itself and kind of evolves over time. Well, in principle, you could do the same thing here. You could have hardware that kind of changes itself and evolves. has been a small community of researchers who have kind of investigated this idea. Nothing really great has come out of it yet, but it's kind of fascinating to think about it. It's kind of dangerous as well. I mean, debugging this kind of thing is impossible. So there's a lot of flexibility here. That's one reason why FPGAs are so interesting. However, of course, this relative flexibility, and I say relative to ASICs, it comes at the expense of larger die for a given function, right? Slower circuits than ASIC for a given function, and more energy per operation for some given function than what you can do with ASIC. Right? So there's a trade-off here. Right? You pay for the flexibility. How much do you pay? Well, this has been studied. I don't have a lot on this I can show. This is something that compares, there's 2 papers here that I used to compare the energy efficiency of CPUs versus ASICs versus FPGAs. And people have studied this over a variety of applications. And this is rough, but roughly speaking, if you look at, this was a study that Mark Horowitz at Stanford did with students, comparing processors, CPUs to ASICs first. Okay. And they showed for some set of functions that they were interested in, that ASIC was about 500 times more energy efficient than the same function executed as code on a CPU, right? Which tells you something. This second paper here is a study that was done in Toronto, studying the difference between energy efficiencies of FPGA versus ASIC. And they showed that there's about a 7x difference. So ASIC is about 7 times more energy efficient for a set of operations than an FPGA. So this is what I meant. The FPGA, there's a premium to be paid for its flexibility, as we'll see. The programmability, the fact that it's programmable kind of slows down the signals and uses more energy and uses more space. There's a similar story for performance. So if you look at modern FPGA designs are run at a few hundred megahertz, usually. And the same design in an ASIC, it would be a few gigahertz. So there's about a factor of 10 in performance typically, or in clock rate at least. And area-wise, depends on the function, but again, it's something like 5 to 10 bigger in area. Okay, so it gives you a rough idea. But still, a much smaller gap between FPGAs and ASICs than the gap between CPUs and ASICs. If by kind of a transitive closure here, FPGAs to CPU is about a 70x gap in energy efficiency. Right? Okay, so that was the flexibility argument. The other interesting thing about FPGAs is their staggering logic capacity growth. Here's a packaged part of the first kind of FPGA. This was from the 80s, as I mentioned, by Xilinx. This is their first part. Is called the 2064. It's 64 logic blocks, an 8x8 array. And it was in that kind of package like that with the little pins, called a DIP, dual inline package. That had 128. I thought it was 8x8. I guess it was 8x16 logic blocks. So logic cells, 128 logic cells. As we'll see, their rule of thumb was there's about 10 logic gate equivalents per logic cell. The amount of logic gate equivalent function you could put into one of their logic cells is about 10 gates. So they said this is about 1,000 gate equivalents. By the time you got to 2011, and I'll show you a more modern part in a minute, but by the time we got to 2011, we had more than 2 million logic cells and 15 million logic gate equivalents. Right? So, of course, this is Moore's law at work here, but the characteristic of FPGAs is that they track Moore's law better than any programmable device. And the reason they do that is they're very regular in their structure. Right? Here's a die photographs of the Vertex FPGA I've been talking about versus the Pentium 4. Remember the Pentium 4? It was a very powerful Intel processor. Look at the difference. Just without knowing anything about this, you see this thing on the left. It looks like a much simpler type of device to manufacture. It's more like a memory part. FPGA, because of the regularity of the structure inside, it's one circuit that's just kind of replicated over and over again. All right? And that makes it easier to manufacture, easier to scale down, easier to take advantage of Moore's law. So it was, and there's a simple scaling thing with FPGAs. You just take the same architecture essentially and make it bigger. So if you had an array that was 8 by 16, and then next year you go 32 by 32, and then 64 by 64, and it just kept growing. You just make bigger and bigger arrays. It's because it's very regular structure. All right. So, but that's not all that happened. So the fabrics, or the reconfigurable array part of FPGAs, got bigger and got bigger. But that's really only part of the story. The manufacturers started adding extra functionality, like memory blocks. Okay. Once FPGAs got big enough that they could do interesting computation, then you need memory to store results, right? So it became more important to add memory blocks and other things, other hard functions like bus interfaces, PCIe interfaces, DRAM controllers for external memory, right? And all the way till we get to the Zinc is the one I showed you on the project board, that pink board. This is kind of a reconfigurable system on a chip. This has the programmable logic in this diagram here, but it has PCIe interfaces. It has 2 ARM cores, ARM Cortex A7 cores, and then memory control, DRAM controllers, UARTs, DMA engines, a bunch of other peripheral stuff. Right? So it's a very general purpose chip in terms of it's got software. You can run Linux here, but then you have all this reconfigurable logic off to the side that you can use for building accelerated functions. Right. And this is more typical of a modern FPGA. Some of the other things you see on all FPGAs these days is SRAM blocks, as I mentioned. These are big blocks of memory, which are more dense. There's more per unit, more bits per unit area than you could get out of flip-flops, as we'll talk later when we talk about memory blocks. And there's ALUs, which are special arithmetic logic units, right, that are available, right, to the user. Ethernet MACs and PHYs, PCIe physical layer connections, right, high-speed, SerDes high-speed input-output. Okay, so they've gotten pretty complicated, lots of functionality. But the unifying idea is still that there's lots of, on FPGAs, lots of programmable logic. And this is logic that is these logic blocks plus the interconnect, which can be configured to do any function that you want. Okay, so we'll talk about FPGA internals and how we get the functionality from logic blocks and interconnect. Somebody asked me a question. Come on. No questions? All right. Okay, so I'm going to talk a little more about the internals. I think it's important to know how they work, how FPGAs work. Just a little bit of a review or background for what I'm going to talk about. Multiplexer we've talked about already. We're going to see multiplexers again inside FPGAs as part of the fabric. That's a 4-to-1 multiplexer, has 2 select bits. So in general, a multiplexer is a combinational logic circuit that chooses between 2 to the n inputs under the control of n control signals. Right? So here n is 2, 2 to the n is 4. 4 inputs, 1 output. I'm also going to talk about latches. Now, we've talked about flip-flops. There's a similar idea called a latch. And as we'll see later, flip-flops are actually built out of latches. But this is a more primitive element. A latch is similar to a storage cell, SRAM storage cell. It's a place to store a bit. And the way it works is There's cross-coupled, so-called cross-coupled inverters. There's two inverters that are in a endless, in a ring here. And the reason we do this, if we want to store a value, we put that value here, and it gets inverted and sent over here, and then gets inverted and sent back. So it gets reinforced. So this is like the idea of restoring logic gates, only in a feedback loop, so that any noise in here, if this signal gets disturbed at all, it'll get reinforced back to its original value. So this is a very stable way in CMOS to store a value, assuming you can get the value that you want onto this node. Right? Then it'll be held, as long as the power stays on, it'll be a very robust remembering of that value. If you want to change the value, then you have to change the value on that node, which means you have to fight against this inverter there. But we'll talk a little bit later about how to do that. But typically, we use a transistor here that can be used to load a new value in. Right? And this has to be strong enough to override this feedback here. Okay. So this is a very common thing. We see it in SRAMs. We see it in FPGAs, as we'll see, as a latch, a place to store a bit. Okay, so the key to FPGAs is how the programmability works. So as we said, FPGA programming allows users to, one, define the function of the configurable logic blocks, or the logic blocks. Two, to establish the interconnection paths between the CLBs, or logic blocks. And three, set other options like choosing which clock to use per flip-flop, choosing how flip-flops get reset, some characteristics in the inputs. Like the pins on FPGA, the connections to the outside world, they have to be programmed to be either an input or an output. Right? And a user can control for each one, is it an input or output, and what voltage levels does it drive, and what voltage levels is it sensitive to, so that it can be a general chip that can interface to other kinds of external chips. Most FPGAs these days have what the manufacturers call SRAM-based programming. And when they say SRAM-based, it means they use a latch like I showed on the last slide, this latch that looks like an SRAM cell. It really has very little to do with SRAM, so it's kind of confusing, but they call it SRAM-based programmability. It really means it uses a latch to program. And the way this works is mainly the programmability is going to define connections between logic blocks. So if I want to make a connection from the output of this logic block to the input of that logic block, what I could do is make a connection at this cross point here so that that signal gets driven onto that wire. And then if I have a range so that there's a connection between this wire and this wire, then we'll have a complete path that goes from here. So before you use the chip, you'll put some bits in here that will program that path in if you want to have a connection between those two logic cells. Right. Likewise, we need to define what the function of each logic block is. Okay. And I'll show you how that works in a minute, but that also uses latches. First, we'll talk about the interconnection points. So we call these programmable cross points in this case. Right. More generally, they're programmable interconnection points. Right. So one way to do that is to use, again, a MOSFET, MOS transistor, which can act like a switch, as you recall, hopefully, from another class. So this is, if you put a high voltage of 1 here, this makes essentially makes a short circuit, a low resistance path between these two wires. If you put a 0 here, it makes an open circuit, a high impedance path, or a high resistance path between those two wires, so a signal can't flow between those two paths. So it acts like a switch. So we can turn the switch on and off by what we put in the latch. So if the latch is holding a 1, then that switch is closed, and there's a connection between those two wires. If we put a 0 in the latch, that switch is open, and the wires don't communicate with one another. So that's the way that the cross-point switches are built inside the FPGA. Right. This is a nice way to do it because you can change it. Right? Once you set that switch, it's not permanent. If you reset it or put different bit inside the latch, you can change whether or not that switch is closed. So So every time you program it, you set the switches in a different configuration if you want a different circuit in there. The bad thing is it's volatile, which means if you turn the power off, it forgets. So you have to store all these configuration bits somewhere on the disk or in a memory, a permanent memory on the board. A lot of FPGAs are programmed this way. When the power comes on, the programming bits are moved automatically from EEPROM or flash memory on the board over into the FPGA to program the FPGA. In the boards in the lab, we don't do that. We program the FPGAs from a file, so some software that sends it over a USB cable, sends the bits over to the FPGA to program the FPGA, right? Which is the mode for debugging. But once it's debugged and you're going to embed that in a product like a scooter or something, you want, as soon as you turn it on, you want the program to go into the FPGA. So that's one thing there. Also, this is relatively large, as we'll see. To make a connection between two wires, if this were on an ASIC, we would just put a via there, make a cut through the insulator, and let the metal flow down there during manufacturing. It would make the connection in a very small area. The area would be no bigger than the cross-section of the two wires. Here you have this extra stuff underneath to get the transistor and to store the latch. The latch has at least 5 transistors in it. It has the 2 inverters plus the other transistor for loading the value. So this is what I mean about the overhead. To make this connection be programmable and not just a fixed connection, it comes with the cost of extra transistors. And the impedance or the resistance of this connection on an ASIC is low. It's just the metal resistance. On the FPGA, you have the additional resistance of the channel of the transistor, right, which slows, that extra resistance slows down the signal and causes more area, right? So that's part of the cost. But it's flexible. So, all right, so that's cross points. We'll talk about the logic blocks in a few minutes, but I'm going to say a little more about the user programmability. I mentioned that the bits can get sent into the FPGA to program it, to define the interconnection cross point routing, where how the signals are going to move from logic block to logic block, and also the function of the logic blocks. The way the bits come in, so the latches store, the internal latches store the configuration. Here I showed a set of latches, these little squares here. Each one has a load signal, a data signal, and the queue. The queue is what's used to control a switch, or it has a different function in the logic block, which I'll show you in a minute. This configuration, the set of bits that defines the program or the configuration of the FPGA is called the bit stream. It's called a bit stream because it's typically loaded 1 bit at a time in a bit serial fashion. This is a typical way it works. There's variations on this, but there'll be some way to, from the outside on the board, a way to send bits in 1 bit at a time, and they'll get clocked in through the shifter here. This is just a shifter, just a set of flip-flops that are cascaded in this manner. Once they're all filled up, then they can be transferred to whichever column they're needed in the chip, right? Typically, it would be programmed in order, so the bits will come in here, then they move here, then they'll come in here, move here, and then come in and move here. So you kind of load up 1 column at a time in the FPGA. It would be one kind of typical way to do it, and the bits are coming in 1 at a time. And those bits, like I said, get stored in external memory or on the disk or somewhere. There's this notion of partial reconfiguration. You can see that if you have this kind of mechanism here, you don't necessarily have to reprogram the whole chip every time. You could program just some set of columns, right? And there's other FPGAs that allow you just to program different isolated portion of the chip. So you can leave the programming in one part and change the programming in another part. That's called partial reconfiguration. And then there's this, I mentioned, dynamic or runtime reconfiguration you can program while the chip is running, right? Kind of in the background. And some chips allow that. The most commonly, though, the entire device is programmed when the system is booted, as I mentioned. So the board will be booted, and then all the bits will come in through the control of a microprocessor or some flash memory and program the whole FPGA. And then it'll be ready to go. There'll be a reset sequence usually to reset all the flip-flops and all the state. Okay, now I'm going to look, we're going to go, remember back here, you have this model in mind, you have all these connections. So we talked about how to make these cross-point connections, right? How they're fabricated on the chip with switches and latches. The switches are just MOSFETs. So now we're going to look inside a logic cell. And we need a logic cell to be designed in a way to give us flexibility. So we can let it be anything we want. So what we're going to do if we have some large design we want to fit on the FPGA, we're going to cut it up into pieces so that each piece will fit inside one of these logic cells. Right? And then we'll wire them together. And I'll talk about how they're cut up later. But for now, let's look at what's inside the logic cells. So this is a simplified logic block. Later, I'll show you some less simplified ones, but this gives you the basic concept. Okay, it's kind of a strange thing at first. So you have this thing, which is, in my example here, it's 4-input lookup table. There's a flip-flop here, there's a multiplexer here, and there's another latch there. Okay. So this lookup table implements combinational logic function. And we can use this to make, in this case, any function of 4 inputs by setting some latches that are inside this. And I'll show you how that works in a second. And then there's an optional flip-flop here. The reason this mux is here in this case is so that the user, by setting that latch, can decide if the output is the output of this lookup table or the output is the output of the registered version, the stored version of that output. Right. So this gives a way to introduce flip-flops into the design where needed by programming in whether or not to use that flip-flop in this particular place. All right. The function in the LUT is defined by the configuration bit stream. Inside the LUT, it looks like this. This is a picture of my 4-input LUT, okay, lookup table. It is a lookup table. The table is here, and we look it up. We look up the answer to this function, okay, using a multiplexer. So here for a 4 LUT, there's 16 latches. And there's a 16-to-1 multiplexer that has 4 inputs. Those inputs to the LUT are the inputs to the multiplexer. The n-bit LUT is implemented as a 2 to the n by 1 memory. Okay, so the input chooses one of 2 to the n memory locations. The memory locations, these latches that I discussed previously. Right? And the inputs to the mux control are the logic block inputs. Okay. So what this means, what this results in is a general purpose logic gate. This combination here can be turned into any Boolean function of 4 inputs by putting the proper values in the latches. I'll show you maybe an easier way to understand that. So this nLUT is a direct implementation of a function truth table. Okay? We've talked about truth tables before, where what we do is we define a function by listing all the possible input combinations and what the value for the function should be for each input combination. Well, this is exactly the way the LUT works, because what we do is we store in those latches the value of the function for each input combination, and the multiplexer then chooses which latch to send to the output based on the input combination, right? So if you go back here, this is like the column of the truth table that holds the value of the function, right? So this is the value of the function when the inputs are all 0, and we choose this one to go out. This is the value of the function when that input's a 1 and the rest are 0, and that one gets chosen to go out, et cetera, et cetera. Right. So it implements this table, and that's why it's called a lookup table. It's a direct implementation of a lookup table. And the nice thing about it is any function of 4 inputs can be implemented with this 4 LUT. Right. So here's a simpler example. If you had a 2-LUT, for instance, a 2-input LUT, that means it would have 2 to the 2 or 4 internal latches. And those internal latches are used to hold these values that are the right-hand column in the truth table. So if I wanted to turn a 2-LUT into an AND gate, I'd load this pattern into the latches. And then the multiplexer, in this case it would be a 4-to-1 multiplexer, would choose which output to send based on what the input combination is. So the 2-LUT implements any function of 2 inputs. How many of these are there? Isn't this a homework problem? This week's homework problem. You don't know?
No, last week's homework problem.
Oh, was it last week's? Oh, okay. So, but we didn't post the solution yet, but we can talk about it. Since you had to turn it in last night, I hope everybody turned it in. The new homework is out, by the way. So, yeah.
Is there anything special inside the FPGA multiplexer that's different than a normal one?
No, I mean, functionally, it's just like a normal multiplexer. It's made to be fast from, since these values are stored in here when you program the FPGA. So they're there very early. So this mux is designed so that the delay from here to the output is minimized, rather than with some muxes where we design it where the delay from here to here is minimized. But since these are here early, we don't have to optimize that path. The critical path, or the path that's going to determine the speed of the LUT, is the path from the control input to the output. Kind of a subtle point, but we'll talk about that more later when we talk about muxes. Okay, so how many functions of 2 inputs are there? 2 to the, yeah, and it is 2 in this case. So it's 2 to the 4 or 16 functions. Where are those functions? That's weird. Did this? Oh, I have it yet later. Okay. Yeah, so there's 16 different ways to populate all those, that right-hand column. So that means there's 16 different functions of 2 inputs. For 4-input LUT, there's 2 to the 4, which is 2 to the 16th. It's 2 to the 16th. Is that 64,000, right? There's a lot of different functions that can be implemented in this rather unassuming little thing here, right? So it's probably overkill, actually. You probably don't need that many functions to be useful, but it can implement all those. Okay, so that's the basic idea behind the internals of the FPGA. You can see now how you can make programmable interconnections, and you can see how you can make logic blocks that can be any functions that we want. And so the goal of the tools then will be, after the tools take your Verilog and synthesize it down into logic gates, then this big network of logic gates is cut up into subfunctions, where each subfunction, which is a collection of logic gates, can fit inside one of the LUTs. Right? So this is the generic kind of flow here. You enter your design somehow. Usually these days you create your design using Verilog or VHDL, some other hardware description language. And then the design is implemented. There's a logic synthesis tool, which will take the HDL and parse it and turn it into basically a gate level representation. And then that gate level representation, which is a large net list, will get partitioned, placed, and routed. Okay. So partitioning is the process of cutting it up into smaller pieces or subfunctions. The placement is to figure out where each one of those goes on the chip. And then the routing is the process of making the connection, planning the connection route between the various logic blocks. Right. And then the tool, after it does all that, it can create a bit stream, which will program the device to implement its results from the partitioning, placing, and routing. Right. And then once you have that, you can test it. You can verify your design. This is done. The tools that do this step, the logic synthesis, the partitioning, placement, and routing, they'll give you an estimated cost, performance, and power, even before it gets mapped onto the FPGA, because it knows approximately how much space and what the critical delay will be and approximately how much power. Right? So you can use that to iterate, change your design a little bit. You can use a simulator to check the function. There's simulators that will simulate at various levels, either at the Verilog level or at the mapped level. And then eventually you can load the design onto the FPGA and check it out in the real world. Blink some lights, connect to video. There are some tools that let you build a logic scope on the FPGA. Along with your design, the tools will embed in what looks like a logic analyzer so you can watch some of the signals change inside the FPGA, which is kind of a nice way to debug it. You get access to and visibility to some of the internal signals to help debug your design. All right. So I'm going to go into more details on what the tools do. And we'll do a hand example here. Just to give you a kind of a feel for how the tools work. So I presented here a simplified FPGA structure. The blocks here are logic blocks. We've got a bunch of wires here in some interesting configuration, which in some ways is typical of what you see on FPGAs. This idea of the segmented wires. You have some wires that go a long distance. You have some wires that go just a short distance. And so the tools understand the structure of the FPGA, and they can route according to the available wires. Right. Here's an example circuit. Doesn't matter. You don't have to worry about what this does right now. It's got some ands and ors and an inverter over there, and it has two flip-flops here. And they're connected in this interesting way. Right. So let's say our goal is to map this onto here. So the combinational logic has to be, we say, covered by the 4 LUTs. 4 input, 1 output LUT. Right. So we have to figure out how to use the LUTs in order to implement this logic function. And then the flip-flops that are in here have to map to the flip-flops that are inside the logic cell. So we're going to use my simplified logic cell here that has a 4 LUT and a single flip-flop. So we have to map these flip-flops to flip-flops that actually, this is the flip-flops in our design, we have to map them to flip-flops that actually exist on this FPGA fabric. And then do some placement, and the placement is going to try to minimize the wiring. Right? 2 blocks that connect with one another, like here, there's this feedback between these 2 blocks. You'd like them to be close to one another on the chip to minimize the length of wire that connects them, because longer wires have longer delay and take more power and take more chip area. So everything is better if you can understand kind of the locality of the connections. It's not always possible. This is an interesting problem, and the same thing comes up in the ASIC world. The circuits we design tend not to be planar, and they tend not to be 2-dimensional. They tend to be, lots of things are close, but in many dimensions. So the problem is to take this high dimensionality graph and smash it down into 2 dimensions. So things that are close in your design may end up not being very close on the surface of the chip, because the surface of the chip is 2 dimensions, and we're smashing this high dimensionality thing down onto it. But the tools do the best they can. Okay, we'll assume, which is true with FPGAs, that VDD and ground is pre-wired, so we don't have to wire up ground and VDD connections. Those go everywhere automatically. And clock goes everywhere, and reset is going everywhere. All right. So that's the nice thing about FPGAs. There's some basic services or infrastructure that is kind of permanently there. Okay, so let's look at first how to do the partitioning. So look at the circuit here. One thing you could do is, if you wanted to, is just to choose to map each logic gate into one of the LUTs. Okay, our LUT can do any function of 4 inputs. We could just connect 2 of the inputs to ground and use the other 2 inputs, and that LUT could implement that function. Right? It would be kind of a waste, but it would be an easy way to do it. It would just have, and same thing for the inverter, we could have whatever that is, 7 LUTs. But it'd be kind of wasteful. If we're going to use a LUT, we might as well get as much functionality into it as possible. So one obvious thing to do would be to look at and cut it like here. If you cut it here, you have a single output coming out. You cut that input, that's one input, that's one input, that's one input, that's one input. Right. And then you could put that into a LUT, a 4 LUT. As long as you don't, it'll fit as long as you have no more than 4 inputs into this partition, right, and a single output. Then we'd need another LUT for that inverter, though. Right? So if we're going to partition this off, we might as well include that inverter in it. Right? And that's a more optimal way of doing it. In fact, we're going to partition it this way. Well, I included the flip-flop here because we can get the flip-flop. It's in the logic cell as well. But look at the inputs. We have a single input there, single input there, single input here that comes from over here, and that's all. So this one is a partitioning. It actually only uses 3 of the inputs to the LUT, right? But it'll fit. This function, complete function, will fit inside that LUT. Now we need to cover this stuff. Now, unfortunately, this inverter, which now is included in here, has this output that comes here. We can only have a single output out of a LUT, and we're using it here for that connection there. So we can't get this output out here. But what we can do is duplicate that inverter, include that in the other partitioning as well. So we take that in the other partition. There's no reason that says we can't just effectively duplicate that inverter and have it go in both LUTs. Okay. If that's the most efficient thing to do, in this case it is. All right, so then this partition has 1 input from here, 1 input from here, 1 input from here. It's the same as the other, uses 3 inputs. The other LUT input would just get tied to some constant 0 or something like that. Effectively doesn't get used. All right, so that gives us kind of the optimal partitioning of this thing. Remember, the rules for LUT partitioning is as long as you have the right number of inputs and the right number of output, typically 1, you can include as many logic gates as possible. Right? In fact, including as many as possible means you're going to end up with a smaller number of LUTs than if you include fewer than possible. Right? So you want to maximize the amount of logic you put into one LUT. Okay, the next step then is somehow we have to do the placement. So let's just say arbitrarily we put this partition B there, and then we'll put A next to it, close, so they can communicate. And then we have to assign an input. Let's say this input comes from the outside world. We can just say it's going to come in on this wire here. So we'll arbitrarily assign that here, and then make it the connection. So then the tool would figure out, I've got to get in to both of these logic blocks. So we're going to wire it up that way, and then wire it here, make a cross connection here, make a cross connection there, and then we get it into that logic block. And then there's the other wiring here. We have a path that goes from A to B. That's this signal here, comes out here, goes in over there. We can make that one there, up on top. And then there's a connection from B to A. That's going the other way. And then the output, we use this wire here because it goes to the periphery. And then that can be assigned out. Right. So at that point, we have partitioned it, we placed it, and we routed it. And then the tool would go and figure out what all the bits are to set in what positions in order to implement this. So when you program it, this is the function you would get. So 2 partitions, each has single output, no more than 4 inputs, and no more than 1 flip-flop. Okay, in this case, the inverter goes in both partitions. And I mentioned this partition can be arbitrarily large as long as it has not more than 4 inputs in this case and 1 output, and not more than 1 flip-flop. Right. So that single example, but I think it gives you a feel for how these tools work. They do this on a large scale, very large devices, very large circuits. They can take a long time to do it. You will learn when you're in the FPGA lab. Even though designing with FPGAs is faster than ASICs, the tools can take hours to do their job because it's hard to figure out how to place all the cells to get the minimal delay, right? This is this multidimensionality problem. There's lots of connections, and figuring out which pieces need to go close to which other pieces in order to minimize the delay is a hard job. And so it tries lots of combinations, and it can run for hours, sometimes overnight. Probably not the designs we do in the lab here. The designs we're doing probably should take less than an hour, I believe. Okay, yes?
Is there an option for I don't really care about delay or power efficiency. I just want to get it on the board and try it out as quickly as possible.
Sadly, not really. We've been asking for it for years, but there doesn't seem to be a way to really make it go much faster by relaxing the constraints. So you can tweak it a little bit, but there's no really quick and dirty mode, unfortunately. So this is idealized. Let me show you what a real logic cell and interconnection looks like. This is from actually an older Xilinx FPGA. The logic block is here with its inputs and outputs. This is the wiring that's associated with one logic block. So this would be a tile, and this gets replicated. This is the complex, shows you all the different variety of wires. FPGAs are mainly wires, if you look at these chips. Most of the area is in the wires. Because if there's not a lot of wires, it becomes really, really hard. It's even harder for the tools to do what they need to do. Okay. So there's lots of different wiring resources. Some wires are short, some are long. There's different intermediate lengths. And then you have switches here that allow signals to come and turn the corner. You got switches here that allow connections into the logic block and out of the logic block. All right. So that's more representative of what real FPGA wiring looks like. So it's not something you want to do manually. You really want the tools to do this for you. So back to this die photograph. I think I mentioned this. This just shows the different types of resources available. The stuff I've been talking about with the interconnection and the logic blocks, that's all these green regions here. Right? And this chip is augmented with clocking circuits here, which are used for generating clock signals. I/O input and output circuits here. These ALUs, which we'll talk about later, and RAM blocks, memory blocks. Right? Everything is kind of, for these Xilinx FPGAs, everything is kind of in this column type configuration. Everything is done in columns. Here's kind of a state of the art. These are actually last year's, but they're still pretty current. FPGAs. These are the large ones. There's a whole family of FPGAs and small. You can buy small ones for $10. You can buy large ones for $10,000, right, or more. This is the higher end. Just to give you an idea of what the state of the art is. We'll look at this device here, which is the biggest one. The number of CLB LUTs is, this is in thousands. So there's 1,300,000 CLBs or LUTs in this device. Right, so it's a lot of logic resources. So if you think each LUT is about 10 logic gates, then that's something like more than 10 million logic gates. So you can implement a very large system on this FPGA. What else? And memory, it has built-in memory. We look at block RAM, this one, 70 megabits of memory right inside the FPGA. Plus it has interfaces for external DRAM if you need more DRAM. Okay, so that's kind of state of the art. There's some, this is 16 nanometer. There's some 7 nanometer FPGAs that have just been announced, which are beginning to come out now. So, and those have other features and even more fabric. So I'm going to show you some more details of commercial FPGAs. So this is the way that on the Xilinx FPGA or most Xilinx FPGAs, what the organization is. The CLB is actually decomposed into 2 slices. I'll show you what's inside a slice. And then these are the connections out to the switching, the configurable wiring. And then there's usually connections up to neighboring CLBs, so some direct connections. Right? The primitive is, for Xilinx FPGAs, is a 5-LUT, not a 4-LUT. Okay. So this is 4 input LUT. Kind of shown here. You got those 4 inputs and you have a single output. And of course, this is implemented as a 5-to-1 multiplexer and 2 to the 5 or 32 latches. And this implements any 5-input logic function. Now, this is kind of an important concept here. So they put 5 LUTs together, and you can combine them under user control to make a 6-LUT. So the way this works is there's an extra multiplexer here, right, which can be used to either this multiplexer under control of this extra input can choose the output of this LUT or the output of this LUT. And if you think about that, it's kind of like taking a 5-input truth table, another 5-input truth table, and then choosing between the 2 based on an extra input bit. So now we've made a 6-input truth table, effectively, with this idea. So this is kind of a general concept in how you make bigger LUTs out of smaller LUTs, is you add one extra level of multiplexing here. There's multiplexers in here anyways, but you're just kind of extending the multiplexer to one more layer and then making this LUT be twice as big. So if you want to go from 4-LUT to 6-LUT, now you go from, or 5-LUT to 6-LUT, you're going to go from 32 latches in here, 32 latches in here, extra multiplexer, extra input, and now you get a 6-LUT. So this is a level programmability that's available on these devices. So if you have functions that are better mapped as a 6-LUT, then you can map it as a 6-LUT. So then these combination, these 6-LUT, 5-LUT, 6-LUT things are combined to make a slice. Right? So it's 4 6-LUTs are put together with 4 flip-flops. So there's 1 flip-flop for every pair of 5-LUTs or for every 6-LUT. Right. And as remember, we got 2 of these slices per CLB. So the CLB is much more complicated than I've been showing you, because it's 2 of these slices, and each slice has 4 flip-flops and 4 6-LUTs. Right. Now, the slice also adds other features. Right? This is a simplified diagram. The other feature are some more muxes that are here to make even bigger LUTs if you choose to. Right? The outputs of the 6-LUTs are available on the outside. The outputs of the 5-LUTs are available on the outside. But there's also outputs of combined 6-LUTs, which would make a 7-LUT. There's an extra input for that. Right? And down here as well. Right? And there's actually one more multiplexer. You can make it an 8-LUT. So you can use all the 5 LUTs of a slice and make one giant 8-LUT. Right? So the tools choose how to do this for you. Right? It will choose the best mapping for your particular logic circuit. If it's better mapped to an 8-LUT or 2 7-LUTs or 4 6-LUTs or whatever it is. Okay, so I think this is kind of shows all those options. So things are getting more complicated here. There's a interesting thing about FPGAs. You can add and designers figured out you can add this kind of functionality without affecting the area of the chip very much. The CLBs are relatively large already, and there's a lot of the area that's in the wiring. So by adding a little extra logic into the logic self, it makes it more flexible and more useful for the user than there's been a tendency to add that extra functionality. It comes at an incremental cost, but it may be just the right thing for some user, or may be just the right thing for somebody's circuit to run faster. Right? So you see kind of a feature creep in FPGAs over the years. They've gotten more and more complicated as more and more features have been added. Okay, so this is kind of a summary. So far we have a slice here which can be from 5 LUTs to 1 8 LUT. You have outputs that are the combinational outputs and the registered outputs after they've gone through these are the flip-flops. Each flip-flop is configurable in the sense that you can have a clock enable on it. You can choose which clock. There's multiple clock signals that run around the chip. There's optional set and reset signal. I forgot what this one does, reverse. And there's a Q out there. So the registered version and the unregistered version of the outputs from the LUTs are available at the outside. And there's one more thing I wanted to point out, which is there's logic that runs this way through the LUT. And this is used for speeding up addition. Remember we talked about ripple addition, and the thing that slows down ripple addition is the fact that there's a ripple that moves from stage to stage. If that carry logic were implemented in LUTs, it would be slow because you're going from LUT to LUT to LUT. And since addition is so popular, they've built in special circuits that implement the carry chain, that rippling of the carry through the adder. So it can make adders, and show the details here, we'll talk about it more later, but this is extra logic that's in there specifically for speeding up circuits like adders. Incrementers and counters are another example of what gets sped up like this, or comparators can also use this logic. So kind of these iterative serial sequences in space can be sped up with this special logic. And like I said, it's incremental addition to the size of the LUT, but it actually speeds up a lot of circuits dramatically. All right, almost done with this. So if we put it all together, we get this somewhat more complicated looking thing as a slice. This actually describes what we call a slice L. It's a logic slice. About half of the slices on FPGAs are of this type. The other half are slice M's, and they have extra features. And this was a tricky idea that came up probably 15 years ago now. If you think about these LUTs, which are here, the blocks shown here, these are the flip-flops, these are the LUTs. The LUTs have a lot of these latches in there. Okay, the latches are typically set by the configuration bit stream, which defines the function of the logic blocks. Well, those latches look like little memory cells. Right? So if you add extra logic, the circuit out here could read and write those LUTs and treat those LUTs as like little memories. Right? And that's what a slice M does, is to use those latches so that the user circuit can read and write those latches, not just the configuration bit stream. Right. So yeah, so that's about all I wanted to say about it. Is these latches that typically they're written only by the configuration bit stream, right? But in the slice M, where you place the 5 LUTs with circuits that can act like the 5 LUT, but can alternatively be used as use the 32 latches in the 5 LUT as a RAM, or a shift register, or a ROM. Okay. So it adds extra memory resources inside the FPGA. Okay, and then the final thing I was talking about, I said that FPGAs have lots of ALUs in them. And the reason is, and these are ALUs that do add and multiply and logical operations. Now, logical operations are pretty efficient in LUTs, and addition can be made fairly efficient using the LUTs with the carry chains that I talked about. But multiplication, turns out, is a pretty expensive thing to implement using LUTs. And multiplication comes up in a lot of the computation that we do. So there's special blocks inside the FPGA that make multiplication. They're dedicated multiply add blocks. They're called DSP slices. DSP stands for digital signal processing because these were put in initially to make digital signal processing more efficient. If you know about filter design and the kind of stuff you learned in 16B, there's a lot of multiply adds. To make FPGAs efficient for signal processing, they put these DSP blocks in, which are really ALUs. And the ALUs have multiplier right here. In this version, it's a 25-bit by 18-bit multiply. Right? And also has an adder here and logic function block here. So it's a general purpose ALU that also has a multiply function in it. So for those applications that have lots of multiplies and adds, they can take advantage of this and save the LUTs for other functions. And I think just about done. So we're going to continue this. We'll talk about some of these other blocks, like RAM blocks and some of the clocking stuff later in the semester. But for now, that's the overview. So at this point, you should know why FPGAs are interesting, what they look like inside, how they implement your logic, and what the tools do in order to map your circuits into the FPGAs. So that's all I wanted to say. Any more questions? All right, good. So we'll see you on Thursday. The new homework is out. Don't delay. Start looking at it now.